In this video, I'm going to make one more example about using the Gauss Seidel method for solving system of linear equations. So I already made a video about this and it's a pretty good one. It's complete. But I always think that more examples are always welcome, and the more the better. So I'm going to make one more example here. So let's start once again with a system of linear equation. So let's suppose we have our matrix A, which is 4, -1, 0, 0, and we have -1, 4, -1, 0, and 0, -1, 4, -1, -1, 0, -1, 4. There we go. This is our matrix A. And then we have our vector X with the component. Well, this is a 1, 2, 3, 4, 1, 2, 3, 4. So a 4 by 4 matrix. Now vector X, so we are working in the R4, so the 4-dimension space. Now vector X is of component X, Y, Z, and W, because we are, as I said, in R4. This is equal to C, which is the one that has our values, so of the linear system of equation. So -1, 2, 4, 10. So written in another way, this system of equation is basically just this. So you basically take 4x plus, but we got a minus, so minus y equal to -1, negative x plus 4y minus c equal to 2, negative y plus 4z, I'm sorry, minus w equal 4, and negative x minus z plus 4w is equal to 10. No, there we go. So this is our system of linear equation. So first thing first, I gotta get the components x, y, z, and w from each equation. So I'm not gonna solve the system. I'm just gonna get the components out and get them in function of other variable. So let's just do this. So this is gonna be 4x equal -1 plus y. Then we're gonna have 4y equal 2 plus x plus z, 4z equal to 4 plus y plus w, and 4w, which is 10 plus x plus c. And again, remember, I want to get the variable here. So get equals. I'm just gonna divide, So x is -1 over 4 plus 1 over 4y. Y is 2 over 4. It's gonna be 1 over 2. And then we have plus 1 over 4, just dividing. X plus 1 over 4z. Then we have z equal to 4 over 4, we are lucky, is 1, plus 1 over 4y, plus 1 over 4w, and then we have w, which is 10 over 4, which simplifies to 5 over 2, plus 1 over 4, x plus 1 over 4 z, which is, let me write it down once again because with all the simplifications done. So x is equal to 1 over 4 plus 1 over 4y. And then we have y, which is equal to 1/2 plus 1 over 4x plus 1 over 4z. Then we have z, which is equal to 1 plus 1 over 4 y plus 1 over 4 w. And then we have w, which is 5 over 2 plus 1 over 4, x plus 1 over 4 z. So those are our variable. I basically got x, y, z, and w from each equation. And no, I didn't actually solve anything. I just just got them function of other variables. So from here, I'm going to start with the iteration. So let me just kind of write iteration 1, step 1. As I said in the other video, I basically consider an iteration whenever I get a full iteration cycle for each variable. So people may say, well, hold on a second, this is not actually an iteration, you consider a full iteration. So each step, we consider each step an iteration, which is totally fine, just a different way of saying it. For instance, MATLAB, using a different notation, some textbook use my notation, some other use another notation. It's fine anyway, it's fine. The method is still the same. What matters is when you're gonna get the result. And once again, I'm gonna say that this method is actually pretty repetitive, so it's basically you're gonna apply it over and over again. It's always the same, it doesn't change. So there is nothing fancy or particularly interesting about this method other than doing it on your computer, so on your CPU and so on, because doing it by hand, it's not like you don't generally do this yourself in a piece of paper, but in your either linear algebra or numerical methods class, you may be asked to do it in a piece of paper, so this is why we learn it. After all, we gotta learn it in the first place in order to implement it both on a piece of paper and on MATLAB. So okay, we started with our system of equation. We basically got the x, y, z, and w function of other variable. Now I'm gonna start with the iteration. So let me just write a table here. Not particularly good in writing table. Straight lines alike. Anyway, I'm gonna say those here are the iterations, and here I'm gonna put my values. So iterations are gonna be, when I'm gonna be doing the iteration right here, I'm gonna write the variables. So you can start whenever you want. I mean, you can generally either start from x equals 0 or x equal 1 and so on. So all the variables equal to, I don't know, 1 or 0 and so on. And I go on and on and on with the iteration. If the book or the professor or teacher doesn't actually tell me anything, so I start myself with something random. In this case, since I copied it from the book as well, it was actually saying to start with those values. So negative 0.25, 0.44, 1.11, and 2.72. So those are the values that they basically asked us to start with. So I'm gonna plug those values in. But again, it doesn't actually change anything if you choose different variables. It's just gonna be either faster or slower to converge to our solution, which is still gonna be an approximation. So okay, so I'm basically gonna write the values that we just got here because they gave them to us. But again, I could, starting with x equal 1, y equal 1, and so on, will be totally fine anyway. So I'm gonna start with x equal to negative 0.25, y equal to 0.44, z equal to 1.11, and w equal to 2.72. And I'm also gonna right line because I'm basically charging all the all the values we have here. So this is actually, I mean, it's not, you don't really have to do it, but it's a good way to remember what you're doing. So the reason why I wrote a little line down here is that this way tells me that I gotta get a new x, a new y, a new z, and a new w one by one. So I'm gonna start with a new x. I'm gonna say x is equal to, I'm gonna use this equation here that we just got, okay, this one here, so negative 1 over 4 plus 1 over 4y, but please note that I'm gonna use a new value of y, which is the one that they basically gave, the textbook gave it to us, so 0.44. So let me just write it. So negative 1 over 4 plus 1 over 4 times 0.44. And I know, I shouldn't be, we have fractions and we have 0.44, so we gotta bring everything, we gotta make sure that everything is consistent. So we eventually down the road, we're gonna have to approximate. And I know that for the mathematicians among you, it may sound weird. It does sound weird for me as well. I don't actually like to, approximate, but you gotta do what you gotta do. So it's gonna become well, a negative 0.25 plus 0.25 times 0.44, and this is gonna give us our 0.25 plus 0.11, which is gonna be negative 0.14. So our new value for x is negative 0.14. So let's start with let's go on and go to the iteration 1 step 2. So iteration 1 step 2. So we're gonna basically take this new value right here, and then go on and do the same for y, and using, since y is dependent from x, we're gonna use the new value we just found in order to get the new approximation for y. So let me write the table once again. There we go. Those are our iterations. Those are our values. All right. So we basically got the new value for x, which is negative 0.14. Then we still have y, the same, 0.44. Z equal to 1.11. and w equal to 2.72. So right now I'm just gonna put a line here, write a little line here to those values. I'm gonna charge those values only and not this one, because we already found a new value for x in this iteration 1. So we're at step 2, we're looking for y. Step 3, we're going to be looking for z. Step 4, we're going to be looking for w, and then we're going to go to the next iteration. Okay, so y is actually equal to this equation here I have, which is dependent from a number, so a scalar, and then 1 over 4x, so dependent by x, and 1 over 4z, so it's dependent by z. So let's just write it down. So as I said, we basically have 1/2 plus 1/4 times x, which is negative 0.14, so negative 0.14, plus 1 over 4 z, which is 1.11, so 1.11. There we go. So let's just go on. This is gonna be 0.5 plus 0.25 times negative 0.14 plus 0.25 times 1.11, which is going to give us 0.5 minus 0.03 plus 0.28, which again is going to give us y equal to 0.75. So this is our new value for y, and let's continue. Let's go on. So iteration 1, step 3. And again, as I said, I'm gonna write my table here. As I said, some of you may consider this already iteration 3. It depends on textbook and so on. So it's gonna be our iterations, and those are gonna be our values. So what do we have? Well, I'm gonna just put the new value for y and just copy all the other values. So x is x is equal to negative 0.14, y is equal to 0.75, which is the new value we just found, z is equal to 1.11, and w is equal to 2.72. So this time I'm only gonna charge, so I'm only gonna write the line here on z and w because we're looking for z, whereas step 3. So z is equal to, I'm just gonna look at the equation. So we said that z is equal to 1, a scalar, plus 1 over 4 y plus 1 over 4 w. So we're going to use the initial value for w because we haven't found a new approximation for w yet. And we're going to use the value we just found of y to get a better approximation of z. Okay, so as I said, z is actually going to become 1 plus 1 over 4 times 0.75 plus 1 over 4 times 2.72. Okay, so our z is going to become 1 plus 0.25 times 0.75 plus 0.25 times 2.72. This is gonna become 1 plus 0.19 plus 0.68, which is gonna give us our new approximation of z, which is roughly 187. Okay, now that we got a new approximation for z, we're gonna go on again and go to step 4, find a new approximation for w. So iteration 1, step 4. All right, so just gonna write a new table here. Again, iterations, values. Okay, and I'm basically gonna write down all the values. Again, so x is actually equal to negative 0.14, y is equal to 0.75, z is equal to 1.87, which is the value we have just found, and w is equal to 2.72. And I'm just gonna charge, w because we already found x, y, and z. So w is equal to, let me just see the equation. Okay, a scalar, so 5 over 2 plus 1 over 4x plus 1 over 4z. So I'm gonna use the value for x and z we have found to get a better approximation for w. So We said 5 over 2, which is our scalar, plus 1 over 4 times negative 0.14, which is our value for x, plus 1 over 4 times 187, which is our new value for z we have just found. So 1.87. Okay, so w is going to be 2.5 plus 0.25 times negative 0.14 plus 0.25 times 1.87, which is going to give us 2.5 minus 0.03 plus 0.47, which is going to give us our new approximation of w, which is 2.93. So we have found our new values for x, y, z, and w. I think I'm gonna make one more iteration here. So I'm gonna go to iteration 2 and do all the 4 steps again. And then I'm gonna stop because, you know, it's long and tedious. And as I said, it doesn't really make sense to do it yourself on a piece of paper unless you're asked to do so in exam. Those are methods used in way bigger linear system of equation than this one in R4. So suppose you have a linear system of equation in, I don't know, R27. I want to say, all right, I want to compute this and I want to get a good approximation of all the 27 values in my 27 dimension space. You can do so. I mean, Intel Xeon CPUs are pretty powerful right now, nowadays, so you can do the, you know, just like that. And it's going to be pretty fast. But the idea here is just, you know, doing it for a rather simple system of equations, so a 4-dimension system of equation, in order to show you how it works, so that you're gonna become, you know, a better mathematician and hopefully a better programmer, better coder. Okay, so let's do this all over again. So iteration 2. Let's go on. Iteration 2, step 1. All right. So iteration 2, step 1. I'm gonna write my table here once again. Those are our iterations, and those are our values. So I'm basically gonna do the same. I'm gonna write all the values that we have just found here. So 0.14, y is equal to 0.75, z is equal to 1.87, and w is equal to 2.93, which is the one we just found. And I'm gonna use my blue pen to underline all of them again, because, you know, we just started the iteration 2, so we're step 1. We're gonna find x, y, z, and w again and get a better approximation. Okay, so let's just do this. Let me see what was the equation like for x. So we have negative 1/4 scalar plus 1/4 y, so dependent by y. So negative 1/4 is our scalar plus 1/4 times our new value for y, so 0.75. So this is gonna become negative 0.25 plus 0.25 times 0.75, which is gonna give us negative 0.25 plus 0.19, which is negative 0.06. So this is our new value, our new approximation for x. Let's just go on in a new piece of paper. Let me see if I can get it. Okay. So let's go on. So iteration to step 2. By the way, for those of you that are concerned about the environment and all my stockpiling way of piling up the papers, those are recycled papers, so they're fine, totally fine. Okay, so I'm not wasting them. Okay, so iterations and values. I'm gonna write all the values all over again. So I'm gonna use my new value, negative 0.06. Y is 0.75. Z is 1.87 and W is 2.93. And I'm gonna underline everything but X because we already found X. There we go. So Y is actually, let me see, I'm gonna keep my the equation here. Crap, I cannot read it. Okay, so Y is actually 1 over 2 plus 1 over 4x plus 1 over 4z. So Y is equal to 1 over 2 plus 1 over 4 times negative 0.06, which is our newly found value for x, plus 1 over 4 times 1.87. And this is gonna be 0.5 plus 0.25 times negative 0.06 plus 0.25 times 1.87. It's going to be y equal 0.5 minus 0.01 plus 0.47. It's going to give us our new estimation for y, which is 0.96. I'm going to go on again. So iteration to step 3. Okay, so this is our table. So iteration and values. I'm gonna write the values again. So x is equal to negative 0.06, y is equal to our newly found value, so 0.96. Z is equal to 1.87 and W is equal to 2.93. I'm just gonna charge those two values. I'm gonna load, I'm not gonna reload all of them. I'm gonna load just Z and W because we already found X and Y. So right now we're at step 3, we're almost done, we're close to step 4. We are just gonna, we're looking for a new, better approximation for Z. So what was Z like? Well, Z was 1, so a scalar, plus 1 over 4 Y, so it's dependent by Y, plus 1 over 4 W, so it's dependent by W. So as we said, Z is equal to 1 plus 1 over 4 times 0.96, which is the value for Y we had just found, plus 1 over 4 times 2.93, which is the former value of W we have found. Okay, so Z is actually equal to 1 plus 0.25 times 0.96 plus 0.27 times 2.93. It's going to give us our X value, which is 1 plus 0 0.24 plus 0.73. So our new estimation for z, I'm sorry, is equal to 1.97. Okay. And now we're just gonna go on to iteration 2, step 4. So I'm gonna complete one more step and complete the second iteration. Step 4. Okay. So iterations and values. So x is actually equal to negative 0.06, y is equal to 0.96, z is equal to 1.97, and w is equal to 2.93. I'm just gonna underline and load my w here because we're looking for w at the end of step 4. So let's see what w was dependent for so 5/2, a scalar, plus 1/4, so it's dependent by x, plus 1/4 z, so it's dependent by z. We're going to use the newly found value for x and z to get a better approximation for w once again. So w is 5/2, which is the scalar. By scalar, I always mean number. So if you get this far with the linear algebra, you should probably know this already, but anyway. So 1/4 times 0.06, which is the approximation for x, plus 1/4 times 1.97, which is our new estimation for z. So this is gonna give us our new estimation for w. Just 2.5 plus 0.25 times negative 0.06 plus 0.25 times 1.97. So this is actually 2.5 minus 0.01 plus 0.49, and last but not least, this is 2.98. Okay, so we have just found all our new approximation for all those steps. So all, we started, let's do a little recap now. So we started with a matrix, a vector, and a C. So this is the matrix of the coefficients. This is our vector, so x, y, z, and w of the values we're looking for. Those are the values they're equal to in our system of equation. We basically got x, y, z, and w without solving the linear system of equation in R4 in the 4-dimensional space, but only getting, x in function of other variables, y in function of other variables, z in function of other variables, and w in function of other variables. Then we started with the iteration. The textbook actually gave us those values to start with for our iterations, but it was actually pretty fine to start with any values whatsoever. Like I generally start with a bunch of zeros or a bunch of 1. And so on. It depends. It's just gonna be a matter of how fast it's gonna converge to your solution. So we basically started by writing down all the values, and we started with the iteration. So we basically used the equation we found for x, which is dependent by a scalar, and y. We used the approximation for y to get a new approximation for x. Then we did the same for y, substituting x and z, those x and z values that we have found here, and we have found a better approximation, and then we have done the same for x, and we have done the same for w, and with this we have found all the new values of our first iteration for steps. Then we started the second iteration, so we got step 1, we reloaded all those values. So we use the values that we have just found to get a better approximation once again. So there's approximation for x, a better approximation for y, a better approximation for z, and a better approximation for w. So our values, our final values after two iteration, complete full iterations. So our guess, our estimation is 0.06, y is equal to 0.96, z equal to 1.97, and w equal to 2.93. So this is our final estimation for those values. Eventually you can go on and try yourself and go on like with iteration 3 and iteration 4 and iteration 5 and so on all over again. And eventually you're gonna see that those values are gonna converge more and more precisely to the real solution. So once again, sorry for the boo-boo, nobody stops you from solving this using, I don't know, like the high school formula, or something like the Gauss row reduction, and get a better system of equation, or I don't know, whatever your preferred method, and then find the real solution and then compare them with the solution we have just found in those two iterations, and then go on and on again with iteration 3, 4, 5, and so on. And then you're basically going to see that the values you had just found from the linear system of equation, by solving it properly, like the proper way, are gonna those values that we had just found are gonna converge to the real values. So why is this method useful? Well, this method is actually pretty useful if you have a very, very large system of equation, like as I said, 24-dimensional space with many variables, and you're gonna it will take a lot of time. It will be like close to impossible to find a guess, like an estimation for not a guess, but the real value for each of those, I don't know, 27 variables. But it's going to be way faster to find a guess, which may not be what you're looking for, but is definitely something that you can work with in satisfying times, like satisfying a relatively short amount of time. So remember, computers are fast and computers are your friend, but you got to learn how this method works, because we don't actually have an infinite precise math, and we cannot make all those calculations in a relatively short amount of time, except by using those kind of approximation and sort of tricks and methods. So this is pretty much it. This was the method as I presented it, and I hope it helps as always. I'm going to make one more example about this method.